gave huge hash table sizes, I could get up to like 4 or 5 megabytes allocated and freed.
Okay.
And what I'm wondering is, some bigger applications in video games sometimes use some kind of different memory allocation structure to get more bytes and organize it in some better way. Because I feel like you would run out of memory way. I've tried to allocate more, enough memory to take gigabytes of space, and I can't do it in C for some reason. With Malloc and Free,
So.
I don't know why that. Go ahead.
So the first thing it depends on is what your operating system is. If it's 32 bits, you're definitely going to have a hard time, because 32 bits, right? The memory address space maxes out at 4 gig, and usually only half of that is actually like usable. But if you got a 64-bit operating system, there's some hope of being able to allocate more space. But there is a limit to how big a chunk Malloc will give you in one block. And if you need more space than Malloc will give you, you probably could be organizing your memory into some kind of structure, right? For example, if Malloc will only give you, say, 2 megabytes, right? Well, if you made a linked list of nodes with 2 megabytes of data on each node, you could have, umpteen megabytes or gigabytes of storage that you're using.
Now, when you say gives you 2 megabytes, you mean in a single malloc statement?
Right.
Okay.
Because a single malloc, it's going to say, here's a chunk of consecutive memory locations reserved for you. And it's kind of like on a hard drive trying to find a block of consecutive memory. It gets really hard because our drives get fragmented, but we can still have a really huge file. It's just that the blocks of that file aren't contiguous anymore.
This would be a really interesting test. Now that you bring up that there's a limit to how much Malloc can allocate in one, I didn't know that. So it'd be interesting to do a test of how many times can I allocate 2 megabytes before it just tells me no more space.
I would say just don't do it on the server, though. Do it on a virtual box.
All right.
Because usually when you run out of memory, your machine will crash. But on a virtual box, who cares?
I've got 32 gigabytes in my system. It'd be funny to try to get half of that or something.
Yeah. So I'm showing like 16 gigabytes of memory available on this system right now. Most of it in use. But I'm that's physical memory, I believe, and there's virtual memory on top of that, and the virtual memory theoretically, is unlimited up to the size of your hard drive, but most operating systems don't get close to that limit.
I think the Windows equivalent of a swap file is some fake 480 terabytes or whatever.
Yeah. And you can also try Googling and see what people say about, what's the largest block I can malloc. And there's probably a lot of opinions and maybe some answers out there.
It'd be interesting to try here too, in a non-garbage collected language, because I think if you try to get away with that in something like Java or C#, it would start garbage collecting at a certain point, right?
Yeah, and Java has limits built into how much memory it'll use, but when you run a program with Java, you can put I think it's a -mx switch on the Java command to say, hey, you can use this much memory, and so you can fiddle with that.
You're saying when you're calling the program, you put Java-MX and then whatever it's called?
Yeah, I don't know if it's MX. One of those is uppercase. XM.
Okay.
And then XMX, and then the number of bytes in the allocation pool. Yeah.
But you can run Java from Bash?
Oh yeah, you can run
Linux?
Yeah, definitely.
Oh, gosh, I didn't know that.
Yeah, there's a Java command.
PowerShell to run it, so.
Okay.
You can use C# on Linux now too.
Yeah.
Interesting.
And if you got the development kit, you have access to Java C to compile, and JDM to debug, and all that kind of stuff.
JDM, okay. That'd be helpful in my other class.
Yeah, yeah. All right, cool. Other questions? Oh, there's a good question. Do we have to have comments in PA3? I did not give you a grading rubric for PA3. And so that's a fair question. Do you need comments in there? I think I would be pretty startled if I saw your entire code without any comments. And I would at the least, give you some feedback saying, hey, you really need to comment your code. I don't think I'm going to take off points for that. But I will tell you that, when you get to a university, if you turn in code with no comments, it's probably going to be a problem. And so you may as well get into the habit of it now rather than, after your first 0 in a university course. It's
Now, do they do that so that you specifically know exactly what your code's doing, or is that so they can read it and know what your code is doing?
I think so. When I ask for comments, it's for both of those reasons. It's to help students develop that habit, because it's going to be a requirement, on the job and so on. It's also because I believe it helps in writing the code, especially with longer assignments, to have, information in the code saying what's happening here, instead of having to remember it. And then for me, if the code does not work, but it's well written and well commented, there's a chance I can go in and say, if I just set this equal to null, it no longer seg faults, and now I can test the rest of the code, and guess what? The whole code works perfectly. And the person just forgot to set this to null, and I can give most of the points. Whereas if it's a bunch of left justified stuff with variable names like A, B, C, and I can't figure out what's going on, and it's seg faults, right? It's pretty much a 0. So there's a number of reasons for that. But I think the biggest long-term reason is that commenting your code as you write it will help you with the process of writing it, going back and finding bugs, things like that. It's sort of part of the process. All right. Well, hopefully people are wrapping up PA3 and had over 2 hours of students in office this morning. So I think we got through some good stuff in there. I have office hours tomorrow at 9 o'clock. If you're not able to get PA3 working to your satisfaction and you have slip days left, go ahead and take a slip day and try to come into office hours. But again, if you've got some of it working, it may be better to turn in what you have than to wait and use up slip days. For example, if you're not able to free all the memory, that's going to cost you a few points, but it's not the major part of the program, right? It's an exercise on hash tables, which depends on linked lists. If your command line parsing is off, that's going to cost a few points, but it's not the major theme. So try to optimize your grade, and if you think you've got enough working to get a reasonable grade, I would say go ahead and turn it in on time, rather than dragging it out. And then Monday, Tuesday next week, Tuesday for this class, we're going to start talking about PA4, which will be binary trees. All right. Well, let's get back into talking about trees. So let's start digging into some actual code, and then playing a little more with some recursive algorithms. So we're building a tree. The tree contains nodes. Nodes have some piece of data. They have pointers to children. And so here's a typical example of a tree node. So it's going to have, for example, a left child, which is a pointer to a tree node. Some kind of data field, and the data field that we'll play with today is just going to be an integer. But, you know, it could be a character array. It could be 3 character arrays, like a plate, a first name, and a last name. It could be binary data, but, you know, it's some sort of payload, the thing that's in the node. And then we have a pointer to the right subchild.
So the root node is limited to 2 children nodes.
Yeah, so we're dealing with binary trees, so every node will have at most 2 children. In a general tree, this could be more. When we talk about something called a trie, we'll actually have 26 children on each node. And so we would probably have an array of struct tree node pointers.
Okay. That's what I was going to ask, if that was possible, but...
Yeah, definitely. But we'll keep things a little simpler here, and notice that if we only have 1 child, right, this is just a good old linked list. Right, it's like a binary tree where each node has exactly 1 child, or 0 children. That's a linked list. So linked lists are an example of a tree, but it's a kind of pathological example. All right, so so this is the kind of structure that we'll be playing with. And so, did we talk about binary search trees yet?
Yeah, where it's like every time you narrow your search by half with the log n.
Mm-hmm. Good, good.
Yeah, with like that exact tree too.
Yep, my favorite tree. So, did we talk about the notion that in a binary search tree, if you pick any node, everything to the right of that node is bigger than the node, and everything to the left is smaller? Have we gone over that notion?
I don't think so.
Okay, that's where we left off then. So this is a particular type of binary tree called a binary search tree. So binary tree is just a tree. Everything has, you know, at most 2 children. But in a binary search tree, and these are usually called BSTs, we have this extra property that if you pick any node, everything to the right is larger, everything to the left is smaller. And when I say everything to the right is larger, what I actually mean is the data value of every node to the right is larger than the data value of that root node. But we'll usually just say, you know, this is bigger than that. But really, we're talking about the data values. So this is a BST because, for example, if I pick this 20 node right here, all the stuff to the right of it, which is just a 30, is bigger. All the stuff to the left, which is just a 10, is smaller. If I look at the root of this tree, which is a 40, all the stuff on the right is bigger than 40. All the stuff here on the left is smaller than 40. And since that's true everywhere, this is a BST. Yeah, go ahead.
Is that because if we put stuff inside of it, we're organizing it from left to right, basically?
Exactly. It's going to be a BST because this is how we're going to construct the tree.
Can I ask a devil's advocate question?
Absolutely.
What happens if we have duplicate numbers here?
Let's just not do duplicates.
Okay.
Because it makes things kind of complicated.
Okay, so duplicates are illegal. Gotcha.
Yeah, and if we needed to have duplicates, what I would probably do is make each node a more complex structure. that could store, for example, an integer and then a repetition count of how many times this is stored. And that would let us do everything that we're going to do today without changing any of it, but still store stuff more than once.
Or if you like taking a data structure of, say, ages and there are duplicates in there, you set down the duplicates first, maybe, if you need to.
Yeah. I mean, when you try to insert it, you just say this is already in here. And if it needs to be there, there's probably other information you're storing with it, so you probably have some other fields in each node. But since we're just dealing with integers and we're using that basically as the key to tell us where this is stored, we'll just assume there's no duplicates. All right, so this is a binary search tree. All right, and one of the nice things about a binary search tree is, guess what? We can search it very efficiently. So let me add some more nodes in here. And I'm just kind of putting these in at random. But you can guess it's probably not random. And let's say you want to look for a 56 in this tree. So we want to search for a 56. And we've got a lot of nodes, right? If this was a linked list, we would have a bunch of nodes, and we'd have to start at the beginning and move through and hope that we find a 56 pretty soon. Or if it's not in there, we'd have to go all the way through the list. We don't have to do that with a binary search tree. We can do the following. We're looking for a 56. Let's check the root. Is that a 56? No, it's not. So we're not done yet. But because we know 56 is bigger than the root, if there is a 56 in this tree, it's going to be to the right of the root. And so we can ignore this entire part of the tree. This is what we call pruning the tree. We've just chopped off a whole bunch of it. And instead of having to search through all of these nodes, now we only have to search through these nodes. And so I'll compare a 56 to a 60, and 56 is smaller than 60. It's not at the root, but it can't be to the right of it either, because everything here is bigger than 60, and 60 is bigger than 56. So I can prune off all of that. And
so
now
it's minimizing the loops to jump through to find it?
It's minimizing the loops that you have to jump through to find it. Exactly.
So this kind of reminds me of the game that we made last quarter.
High-low.
Is it basically the same process, except instead of checking like data or the number that the user's inputting, it's looking at the pointers to the struct nodes and checking the data there?
Yep. It's exactly the same thing as playing high-low, and high-low comes up a bunch of times in computer science. And this is one of the cases where it comes up, because what do you do when you play high-low? I'm thinking of a number, and so we would guess, is it 50? And the person says, no, it's bigger than 50. We've just wiped out, 50 possible guesses. And now we've got a smaller space that we have to search. And so we'd guess, we'd guess 75, but here we're guessing 60, and it's like, no, 60 is too big. Well, we can wipe out all the things 60 or bigger. And so we're kind of cutting our problem into smaller pieces each time that we make a guess, each time that we move down and ask, is it this value? And in an ideal case, we'll cut our problem in half each time we do that. And so if you have 100 nodes in your tree, you only have to cut your tree in half 7 times to get down to 1 node. Because 2 to the 7th is bigger than 100. If you have 1,000...
log in is pretty efficient then.
Yeah, this is playing off the efficiency of log n. If you had 1,000 numbers in your tree, you can find your data or decide it's not in your tree with only 10 operations. If you've got 1,000,000 things, it takes you 20 operations. If you've got 1,000,000,000,000 things, it takes you 40 operations. So it's really, really time efficient. So how do we do this, if someone hands us a tree and says, can you find a 56? well, we start there. It's got to be bigger than 40. Here's a 60. It's got to be smaller. It's got to be bigger than 50, bigger than 55, smaller than 58. Hey, there we go. There's our 56. If we search for a 53, same thing, start of the root. It's bigger than 40, it's smaller than 60, it's bigger than 50, it's smaller than 55. Come to the left, there's nothing here. 53 is not in the tree.
It seems like, in another implementation, you could use this to sift out some type of thing and treating each of the nodes like a preposition, right? So, is it greater than 60? Yes. Like you could treat the left and the right as like a preposition. Is it this thing and not this thing? If it is this thing, then you need to search this half of the tree also.
Mm-hmm. That's an interesting way to look at it, and actually there's a version of binary trees called decision trees that we usually talk about in 223. And we can use those to do something like play 20 questions. And it's kind of like what you're describing. This is a generally really useful way to organize information. We find a lot of applications for this kind of tree-like structure. And you can use this for parsing out language. You can use it for evaluating arithmetic expressions. There's lots of things that correlate to this tree-like structure.
Maybe even like autofill for, typing in a message or something.
Yeah.
It sees what you have so far, what are the other words in the dictionary, could be this or not this, and then cut off.
Definitely.
This stuff.
Mm-hmm. So searching is super efficient, right? Start of the root and just move down one way or another, and if you find the number, you're done. But if you get to a point where it says, okay, 53 should be to the left of this, and you look to the left and there's nothing there, you're done, and the answer is 53 is not in the tree. Because if it was in the tree, it would have to be off to the left of 55, and there's nothing there.
Now, if there's nothing there, that means that's pointing to null, basically, right?
It's pointing to null, right?
So you would check if that's null, and if it is, then return not in the list.
Exactly.
Okay.
And when we draw the tree, if we don't put children, that means the child pointer is null. And sometimes when we draw trees, we'll actually put an arrow and we'll say null or nil, but we don't do that for this. But that's
Out of
yeah.
curiosity, so the struct tree node, right? That's gonna have an int data underneath that too, right?
So struct t node right is pointing to another node, and the node it points to will have all three of these fields, a left, a data, and a right.
Okay.
Yeah, but that's how it links up. If you want the data on the right, you go to the right and then grab the data.
Okay, that makes sense.
Yeah, so it's like a fragmented linked list.
Yeah, it's like a pointer to the next node, except you have two pointers to the next node.
You got it.
Okay, alright.
All right, cool. So as easy as searching a binary tree is, it turns out adding to a binary search tree is just about as easy, because suppose I wanted to add 53. Well, I can pretend I'm searching for it. Start here, go to the right. Come here, go to the left. There's a 50, go to the right. There's a 55, go to the left. Hey, there is nothing to the left. Guess what? That's where I can add my 53. Since I should go to the left and there's nothing there, that's 53's spot. And I'm guaranteed this is still a binary search tree. How do I know that? Because I got here by following the requirements of a binary search tree. I'm putting this to the right of 50 because it's bigger than 50. I'm putting it to the left of 55 because it's smaller than 55. And so when I build up my tree from data, as long as I follow this algorithm of, move left or right, and then when you get to a spot where there's nothing there, put your new data there, I'll always have a binary search tree.
And that one would be pretty easy to add too, right? Because you just point 55 at it and leave the other fields to null.
Mm-hmm.
53.
And anytime I add something, it's always going to be in a spot that's currently null. So somebody pick a number that's not already in the
27?
tree. Say again?
27?
27. So start at 40, it's smaller. Go to 20, it's bigger. Go to 30, it's smaller. There's nothing to the left. Put our 27 right there. And so that's effectively how we're going to build binary search trees. We're going to take in data and we're just going to plop it into the right spot as we go.
So what if you wanted to add like 25 now?
So add 25. I'm going to need a finer point pen. So start at the 40, it's smaller. Go to the 20, it's bigger. Go to the 30, it's smaller. Go to the 27, it's smaller than that, but there's nothing to the left. So we put our 25 right here.
Gotcha.
And kind of amazingly, that's always going to work. But our tree is coming out kind of goofy looking, right? We've got, almost nothing over here on this side. We've got, this kind of like linear stuff going here, and this is starting to get, fairly deep, and this stops right here. And so eventually we'll talk about a notion of balance. And a balanced tree, we find like lots of stuff at the top, and it's nice and full and fluffy before it starts to get too tall. When it starts getting too tall without filling in all the stuff above, that becomes an unbalanced tree. And we'll talk a lot about trees and telling if a tree is balanced and what to do about it if it's not. But that's further down the road.
Can are we ever going to get to red-black trees?
We'll probably touch on them. That's one way of dealing with balance. We'll definitely talk about AVL trees, and then if there's time, we'll at least do a high-level pass of red-black trees, which are interesting, and we get to talk about grandchild nodes and aunt and uncle nodes and things like that. So that's a fun. I don't know if I'll do splay trees. And there's a gazillion types of trees out there, and each one has at least one thing about it that is unique and advantageous against others. And it's a fun subject.
My dad's been an engineer for 25 plus years, and he purchased a couple of books on red-black trees, and he could never figure them out. So he really wants to know if I can print them.
Okay. Well, we'll try to at least touch on them, and I have some pretty good resources that do a nice overview of them. They're called red-black trees, by the way, because when the people were trying to figure this out, they wanted to color code the nodes, and they went into the next room to look for colored pencils and pens, and all they could find was black and red. And so that's what they used, and that's the terminology they were tossing around when they were developing it, and that's the name that stuck with it. So
it's satisfying in my mind because I think of like a big checkerboard.
Ah, totally.
So real quick back to this tree, if you did get an input from the user to add 25 again, would you just basically in your add function just have a conditional, right? If it's already there, then don't do anything, just return.
Mm-hmm.
Okay.
Yeah. So if someone said to add 25, I could do a search first and say it's already in there, or I could just go ahead and use my add algorithm, and I go left, I'd go right, I'd go left, I'd go left, and when I get here, should I go left or right? Oh wait, this is already 25, and then at that point I would notice, this is already in the tree, and either just not do anything or delete all the user's files or whatever I want to do at that point. But if I didn't want duplicates, I would probably just do a search up front, and then if it doesn't find it, then I know that I'm going to eventually get to something that's pointing to null, and I'll put it there.
So you could just do like an if, whatever, if the search is, like if it's found, then just return, and then if it's not, then go through the add.
Then go through the add,
so
yeah, exactly.
Kind of like the linked list from the first one.
Yeah, exactly the same idea where we didn't want duplicates, so call search first.
Okay.
All right, so we can build a binary search tree a number of ways, and once we have one, we can search it, and we can also try to print it. So there's this idea of traversal, and when we talk about traversing a data structure, we're talking about going through all the data in the structure in some way. So to traverse an array, we basically just loop over all the indices and print out the contents, for example. To traverse a linked list, we start with the sentinel node, we follow the pointers from one node to another. To traverse a binary tree is a little trickier, because we're going to start at the root. That's the thing we have that gives us access to the tree. But do we go left or right? And we can decide, we're going to go left, but eventually we need to come back and go to the right. So we can start off, we'll just say, yeah, okay, let's just go to the left, and here's a 20. Well, this whole thing is, another tree, and now we've got to decide again, should we go left or right? And maybe I'll go to the left and deal with this data, but at some point I need to come back and go to the right. And then when I'm done with all of this stuff, I need to come back to my original route and go to the right, because first I went to the left. And the deeper we go, the more fingers we need to keep track of where we're going to go back to when we finish traversing, these smaller subtrees. So this is where we break into a new mindset of programming, which we call recursion. And I want to start with the idea of search. And yeah, we can search the tree the way I've described, start at the root and go left or right and so on and so forth. That works great. But there's a completely different approach we can take to searching a tree. And it's based on the observation that in a binary search tree, if what we're looking for is bigger than the root, it's got to be to the right. And if it's smaller than the root, it's got to be to the left. And so here's an idea, and this echoes some of what we did in CSE215 yesterday. We were doing floor tiling. Suppose my job is to search binary trees. And I can search, trees that are this big. And someone says, hey, is there a 53 in this tree? And I say, hold on, let me check. I'll get back to you in an hour. And so I look at this tree and I look at the root and it's a 40. Okay, so the 53 is not at the root. But I also know the 53 is not anywhere over here. 53 can only be in this smaller tree, right? And my original tree, went from here to here. My smaller tree goes from here to here. And so I'm going to call up a friend and I say, hey, I've got a medium-sized tree for you to search. Tell me if there's a 53 in this tree. And if they tell me yes, I'll tell my customer, yes, I found it. And if they tell me no, it's not in this tree, I know it's not in the original tree and I'll say no. All right, how does my friend search this tree for a 53? They look at the root. It's not at the root. All right. It's got to be in this even smaller tree. So they go to the friend that they have who searches really small trees and they say, is there a 53 in here? And that person says, I don't know, let me check. Here's the root. Okay, it's got to be in this tree. They hand this tree to somebody else and say, tell me if there's a 53 here. And that person says, well, okay, hold on a second. They take the left subtree because 53 is smaller. They hand this to someone and say, hey, is there a 53 in this tree? And the person says, yeah, it's at the root. And so they tell the person who hired them yes, they tell the person who hired them yes, and it trickles all the way back until the person I hired says, yes, there is a 53 in this tree, and so I tell my customer, yes, I found a 53. And I never really did a whole lot of work. I didn't move down the tree, I simply did two things. I checked the root, and if it was 53, I would have said yes. But since it wasn't 53, I picked one of the subtrees, the right one, because 53 is bigger than the root, and I asked somebody else to search that for me. And then whatever that came back with, that's the answer I returned. So the trick with tiling the floor was we don't actually have, friends who search smaller trees for us. We're going to do that ourselves. We're just going to change our cap and say, I'm the medium tree searcher. Give me a tree, I'll tell you if the data's in there. So here's what this looks like in code. So here's my search function. It takes a root and it's supposed to return a 1 or a 0. And I can do the following. If root arrow data, I guess I got to tell it what I'm searching for. So I'm searching for num. If root arrow data equals num, then I found your data. It's right at the root. I'll return a 1. Alright, that's the easy case. If the thing I'm looking for happens to be at the root, if I'm looking for a 40 in this tree, I don't have to do any work. I check the root, hey, yeah, 40's in there. But if not, I have to check a subtree, so I'm going to do the following. If data is less than, if num is less than root arrow data, well, all I have to do is search the left subtree. And how am I going to search this left subtree for num? I'm going to use the search function. So I'm going to say search root arrow left, comma, num. And when I call this, it will do something magical to search this left subtree for my number, and I expect this to return a 1 if it is found and a 0 if it's not. And so I'm just going to say, you know, something like found equals this, and I'm going to return found. Alright, and I got one case left. If the root is not equal to number, and number is not smaller than the root, then number must be bigger than the root. So here, search the right subtree. So I'll say found equals search root arrow right for number, and then return found.
Wouldn't we want an else in there for 0 if it's not ever found?
So there's nothing in this code right now that can return a 0. And if you notice that, that should be an alarm that there's a problem. There's something missing probably.
I have a question.
Yeah.
Should this be in a different if statement that says if the number is greater than?
It should be, except that if the number is equal, we'll return. If the number is less than, we'll return. So if we get here, we know the number is bigger than. So I can put a comment in here. Num must be bigger than root arrow data. But we could put an if statement. We could say if num is bigger than root arrow data, and that does no harm. But if we get here, we're guaranteed num is bigger than the root data. So what's missing here is the situation if our number is not found. So suppose we search for a 75. Well, compare it to the root. 75 is bigger. Let's search this tree for 75. Compare 75 to the root. It's bigger. Let's search this tree for 75. Compare it to the root. 75 is bigger. Let's search the right subtree. Well, the right subtree is null. And if I call search with a root that's null, this is going to segfault. Right? I can't dereference null. But if I call search on a tree that's null, I don't have to do any searching. I know the answer. Is my number contained in an empty tree? Absolutely not. And so to save some work, and more importantly to save a segfault, I need one more if statement up here, which says if root is null, then return a 0. And my comment there is the data is not found. And this will actually work. This
I'm a
is
little confused about something though.
okay.
I'm following the code. This can only take place once because it's an if statement. So it would go through the tree one time, and that's it. Would it have to be in a loop for it to be able to go further down?
It does not, and that's part of the magic of this. Because when I call this search function, that's going to go off and start running this whole set of code again. Right?
Oh,
Because
that's
this
fine.
is the search function that I'm calling there and there.
Is there any way to protect against Stack Overflow here, if it's that big? I mean, maybe that's like a silly pie in the sky example of a tree being so big that it could happen, but is there any way to like protect against it maybe?
It's hard to protect against, and we will definitely have recursive cases where we'll run into Stack Overflow. So it's not a frivolous question, but it's generally pretty hard to predict that that's about to happen.
So
Just
Stack Overflow, I'm assuming, is overloading the memory of the
Mhm.
stack.
Every time that we call a function, we use the stack to save temporary variables, to save information about where we are in the function we're leaving, and so on and so forth. And each time we make this call, we use up more stack space. And eventually we can use it all up.
Gotcha. So we'd have to be really, like, there'd have to be a lot of nodes saved that we're searching through, basically.
Right, but there's other algorithms for other uses that we'll encounter where we'll run out of stack space pretty quickly.
You could probably do some sort of math to like figure out how many stacks it's called, how much memory is being used.
Mm-hmm.
Maybe.
So this being a recursive function, it's going to basically take the root as the node that's being called on it, right? So every time you move down, it changes the root.
Exactly.
to the
So
next one.
so root and num, these are local variables, which means that, when I call this, my root is 40. It's right here. And I'll say, is root null? No, it's not. Is the root data equal to num? No, it's not. Let's say I'm searching for 53 again. Is the root data equal to num? No. Is our number less than the root data? No. So we'll come down here to this last line of code, which says search root arrow right, comma num. All right, this whole picture is preserved. It's tucked away in memory, and a new function call is made. And the function call looks like search. And the root that it passes is, the root of this little tree with all this other stuff on it. And we're searching for whatever the number is. And when I make this call...
The subtrees, right?
Yeah.
Okay.
Right, so when I make this call, I'm passing it the root of this subtree, and everything that's currently happening is saved. Right, take a snapshot, tuck it away, and now begin this function from the top, but with this new root, which is pointing to the subtree. And that's going to probably involve making other calls to search and so on and so forth. But in the end, eventually that call to search on this subtree should return a 1 saying there was a 53. And at that point, my original call says, okay, I'll set found equal to 1. I'll return that. It returns a 1. And the person who called me says, hey, the number was in the tree.
This would absolutely be a problem in like Python where, stack limit's 999.
Yeah, and I think that stack limit means different things. I think you can make more than 1,000 calls to yourself, as far as I believe in Python. But I think there's limits to like nesting statements inside other statements, maybe. And so yeah, recursion is essentially a function calling itself from inside the function. That's exactly what recursion is. And so this is doing the same thing as, start here, go to the right, go to the left, go to the right, go to the left. There we are, right? It's achieving the same thing, but from a very different kind of mental place, perspective-wise. We're not thinking of how do we move through the tree, trying to sniff out the truffle that's a 53, right? We're thinking of it in terms of, I am very lazy today. So I'll check to see if my number is at the root. If it is, fine. Otherwise, I'll let somebody else search this. Tell me if you find a 53 or not, and I'll pass on the word. That's the recursive mindset, right? Do a little bit of work, and if that doesn't solve the problem, get something else to solve the problem.
So can I ask you this then? So obviously in our last several assignments, we've been using temporary variables and things like that to store sentinel pointers and stuff. Could you basically use recursion in those to navigate the linked list and stuff a lot easier?
So here's a recursive way to
because I feel like for the linked list program for like searching,
I
feel like recursion would be so much easier to say, is it this one? No, then move on and do the next one.
Yeah, so that's a totally doable approach, right? To search a linked list, see if the first node is the thing you're looking for. If it's not, search the list that first node points to. And if you find it in there, then it's in the list. If you don't, then it's not in the list. If you want to insert into a list, let's say here's a 10 and a 20 and a 30 and a 40, and you want to insert a 15, well, if this first node in the list is bigger, insert right before that. Otherwise, just insert in the list that this is pointing to. Now, it doesn't work very well with lists because of the sentinel nodes. Because the sentinel nodes make it hard to break up the list and treat it exactly like the original list. Because with a sentinel, we have this extra bogus node in the beginning. But with trees, we're not going to have a sentinel node. And that's really the reason we don't have a sentinel in trees, is so we can sort of break the problem up like this. So it sounds like some people have a pretty solid grasp on this concept, which is startling, but that's good. But usually, the first time you encounter recursion, it looks very mysterious, very sort of suspicious.
Kind of looks like magic.
Kind of looks like magic, and usually is pretty frustrating to try to figure out what's going on. And so if you're feeling any of that, right, you are exactly where I expect you to be with recursion at this point. It takes getting used to, but we're going to work through a lot of examples of recursive algorithms, and we'll start putting some code together at the end of today. And with more practice, eventually this starts to feel more and more reasonable. But right now, this can seem kind of spooky, right? Because we're searching the entire tree, but all we're really ever doing is just checking to see if the root matches our number. That's the only comparison we're really making. But it's this idea of breaking the problem into smaller problems and then having somebody solve that. And this is the floor tiling from CSE222B yesterday. Was to tile the 64 by 64 floor, find someone who can do a 32 by 32. Take those solutions to those smaller problems, put them together to solve the bigger one. Well, searching this big tree, I'm breaking it into a problem of searching a smaller tree. And then I take the solution to that to get my solution to this original problem. So that's a recursive search algorithm. And we can use the same kind of idea for the question of how to print the data in a tree, so this idea of traversal. So let me go back to a simpler tree. And we're always going to grab hold of our tree through the root node. And we want to print this out, and we want to print it in a particular order. it turns out with a binary search tree, well, we'll talk about order in a minute. Let's just try to print all the stuff in this tree. And printing the roots... Go ahead.
Wouldn't we need information for depth first, breadth first?
We're going to do what's called a depth first. And we'll talk about breadth first later. But I want to think higher level. Instead of particular algorithms, just think of the general question of how do we print everything in a tree, given this difficulty of, you know, if I start looking at stuff on the left, I've got to come back and look at stuff on the right eventually. And when I get here, if I start going to the left, I got to eventually go to the right of this. And then when I'm done, I've got to go to the right of that. And it feels like there's a lot of stuff we have to keep track of to make sure we get everything in the tree accounted for. But if we think of this recursively, there's an easier way to do this. Because to print the entire contents of the tree, we only have to do three things. We have to print the root node. We know that, but that's easy to do. That's just, you know, printf root arrow data with a %d or something. And then we need to somehow print everything that's here in the left subtree. And then we need to print everything that's in the right subtree. Well, so let's make a function called treePrint, which takes the root of a tree. And this is going to do three things. First thing it's going to do is print root arrow data. That'll take care of this. Well, I don't want to make temporary pointers and remember locations and that kind of stuff. All I want to do is print all the stuff to the left. And I'm going to do that by using this magic function called treePrint. And I'm going to feed it root arrow left. And I'm going to trust that my treePrint function works and will dutifully print the 10, the 20, and the 30 in some order. And at that point, I've printed the root, I've printed all of this stuff. All I have left is to print this stuff on the right, and I'll just use my handy-dandy treePrint function and say treePrint root arrow right. And that's most of what I need. And this starts to get a little trippy. Because here's the mindset. If I believe that my treePrint function will print the contents of a tree, if I really, really believe that, if I really believe that this will print the right subtree and this will print the left subtree, then I guarantee this will print the entire tree. Because, you know, prints the root, prints the right subtree, prints the left subtree, that's the whole tree. Well, you know, if these three steps succeed in printing the tree, my treePrint function works. And since my treePrint function works, you know, these statements do the right thing, and this whole thing prints out the entire tree. And it's almost a circular logic, right? My function works because my function works. Well, it could also be my function doesn't work because my function doesn't work. But if you imagine for a moment that, you know, you've woken up from a dream and you've had an inspiration, you realize that this treePrint function does work to print these subtrees, then you've got no doubt this whole thing will print the original tree. Because it prints the root node, it prints the stuff on the left, it prints the stuff on the right. But how do we know that this will successfully print, say, the stuff on the right? Well, we need to know that it will print out the root node data. Well, that statement's going to definitely do that. But we need to know that when we call treePrint on this thing's left subtree, this little tiny tree with a 50 in it, we need to know that's going to do the right thing. And the same with the right subtree, which is a 70. How do we know that this will work correctly when we pass it a tree containing a single node, which is a 50? Well, it'll print out the root data, that's fine. And then it will call treePrint on null. And the reality is, if we call tree print with a null root, this is going to segfault. But if we call tree print with a null root, do we have to print anything? Absolutely not. There's nothing in the tree to print. So I can avoid that segfault by putting one extra statement up here in the beginning, which says if root equals null, return.
So because we're able to use recursive functions for this, we don't need to have a while loop then, basically.
Right, the while loop is basically kind of happening implicitly in these function calls.
Okay. So you're basically using, by using recursion, you're using basically nested, not loops, but nested statements. So every time it goes to the one list and then it'll back out to the next list, and so on.
Yep.
Okay.
Yeah. And recursion is one of these things where there's different levels of understanding of it. And, you know, even though I'm a big believer in trying to understand everything down to the most fundamental building blocks, recursion doesn't always yield to that kind of quest for understanding. Usually recursion, we treat it from a pretty high level. Do this, do that, you know. And it might look weird for a while, and then it might start to seem reasonable. And if we think about it a little more, it's going to seem completely bizarre and impossible. And then if we start digging into it and we pretend we're a computer and we write down on multiple sheets of paper what happens each time we make a call, we might get to the end and nod our head and say, yeah, I guess it works. And that may start to feel more confident over time, and then all of a sudden we may look at it and say, wait a minute, this is ridiculous. And it's a weird process, trying to sort of grok the idea of recursion. And it's not a linear process. It's not like the more you think about it, the clearer it becomes. In the process of trying to make peace with this, it will sometimes become crystal clear, and then it will sometimes completely fall apart. And trying to explain this to other people is one way to move through that process. And if you want to, you know, discuss this with friends on Discord or whatever, right? That's a really kind of powerful way to force your brain to think about this stuff differently. And that's where you can kind of break out of the, you know, I think I get it, oh wait a minute, I don't. Or this makes no sense, oh wait a minute, it really does. And it takes time. And there's a reason we don't do this until, you know, 15 weeks from graduation at Clark for most people, right? I've known computer science programs where CS101 they teach recursion. And these programs have had, you know, like a 50% dropout rate after the first semester. It's a bizarre concept, right? But we're going to keep working with lots of different examples of this. We'll put some code together, and if it looks really bizarre and wacky, that's okay, right? Just keep working with it. And when it starts to click and make sense, right, enjoy that sensation. And when it stops making sense later, don't worry about that. All right, so that's my recursion pep talk. And the joke is the key to understanding recursion is understanding recursion. And it's true. And you can Google recursion and see what Google says about it. And that's fun. All right. Let me do one more thing and then we'll take a break. So let me talk about something called LNR traversal. So we've got our binary tree. We've got a way to print it. We can print the root by just printing the root. We can print the left and right subtrees using our tree print. This algorithm right here is something that we call NLR traversal. This is also called pre-order. And it's called pre-order because before you print the subtrees, you print the root. So N stands for node, the root node. L is for left subtree, R is for right subtree. And this algorithm is printing the root node, and then the left subtree, and then the right subtree. if I change that algorithm just a little bit, and let me call this algorithm LNR, and it takes a root. And what I'm going to do is, I'll put my if statement. If root is null, return, because there's nothing to print. Otherwise, traverse the left subtree, print the root data, and traverse the right subtree. This gives me what's called an in-order traversal. And if I do this, my data comes out sorted from smallest to largest. And so, for example, you know, if we pick on my favorite tree, right, this will say, okay, first print out everything to the left, and then print out the 40, and then print everything to the right. So first step, we have to print this tree using left node right traversal, LNR. And how do we do that? Well, the root's not null, so first we're going to print this tree using left node right, and then we'll print the root, and then we'll print this tree using left node right. Well, this tree only contains a 10, so we'll traverse the left subtree, which is null, and when we try to traverse a null tree, it'll just return. And then we'll print the root data, that'll print out a 10. And then we'll traverse the right subtree, which is null, that'll just return. So traversing this tree gives us a 10. And then we print out the root data, and then we traverse this tree, and if we go through all those steps, that'll give us a 30. That's the end of step 1, traversing this left subtree. And then we'll print out the root data. And then, last thing we have to do is traverse this subtree. And if you go through the steps, you'll see that, you know, traversing this means traversing this, which will print out a 50, and then print out the root, and then traverse the right subtree. And it comes out in order. And so node left right is called pre-order. Left node right is in order. Traverse the left, print the root node, traverse the right. And there's one other order we can do, which is left right node, and that's called post order. And traverse the left, traverse the right, and then print the root node. So we got 3 different traversal orders we can use. And the in order one is the one that gives us our data in order. All right, so let's do a 4 or 5 minute break, and then I want to start digging into some code. So let's come back at come back in 5 minutes.
something after that bites, and I can't figure out, like cilantro maybe?
There's cilantro.
Mm-hmm.
But it's weird, like Thomas's great tomato taste and then it like pulls it away.
Yeah, totally. You're still drinking coffee. I'll make a cappuccino.
Really?
I will. As soon as I'm done eating here.
Okay.
I was just worried to give you coffee so late, so.
Yeah, you know. We got a long list of stuff to do. And we're gonna be up late doing homework, right?
Mm-hmm.
Be slogging fractions. Conjugating the verbs.
Yeah.
All right, we're back. Let's see. So some questions in chat. Someone said I don't have a problem with understanding recursive functions if they're already designed. I find it nearly impossible to write my own, though. This is also a very normal experience, and it's the analysis versus synthesis question. It's the thing that makes physics so made physics so complex for me, at least. Able to understand a solution when the TA works it out, completely unable to come up with a solution on my own. That was physics for me.
I feel the same way.
Yeah. And it's something that comes with practice, right? Eventually, after you've seen enough solutions and you've hit your head against enough problems trying to come up with your own solutions, eventually it starts to click. But it's something that's got to be, wired in your brain, and we don't have a way to make that wiring happen other than through this sort of, process of seeing a solution, trying to come up with one, and so on. And so with recursion, after you work with enough recursive functions and maybe you make changes to some, examples of recursion, it starts to become a little more feasible to write your own. And then at some point, suddenly you see everything in terms of recursion, and your dog looks like a recursive function, and then it starts to get really fun. but it takes time, but it does come eventually. All right, and then somebody else mentioned in chat, if you re-upload your project to Canvas, it says it renames it to pa3-1.tar or -2. That's not a problem. Don't worry about it. And I asked you to name them pa3.tar, but in fact, when I download them from Canvas, they have some big, long, crazy name anyway. But that's fine. Don't worry about it.
Hey, we could name everything what we wanted to as long as it followed the function names and the executable generated was plate, but what if our main program is just called main?
That's fine. Totally fine.
Okay.
All right. So in yesterday's class, at this point, I talked about some of these other traversal orders and what they do and how they relate to doing things like making a stack-based calculator and such. I'm going to skip over that right now. We're going to have an extra section for this class in about a week because there's a Monday holiday coming up. So I'm skipping a few things, and we'll go back and pick those up in about another week and a half. But I want to go on and take a look at some code related to trees. Say again? No, not this Monday is normal, but the following Monday, I believe, is a holiday.
Oh, okay.
So, yeah, whatever that turns out to be. Don't take my word for it, but I know there's another Monday holiday coming up sometime. So let's take a look at some code. All right, so we're going to play around with some trees. And let me bring this stuff back. All right, so we're gonna want a tree node. So I'll have a left. I'll have an integer data. I'll have a right. Don't forget your semicolon at the end here. C is picky about that, and it can cause lots of stray errors if you don't have that. Now, when I did this on paper, I think I put the data first, maybe, I don't know. The order of these things is significant. As long as you're consistent, it doesn't matter what order you put these in. But if I have a main program and I declare a struct node like this, and then I have, say a function, and I declare a struct node like that, all heck will break loose. Right? That will not work, but it won't give me any warnings when I compile. But strange things will happen when I start running. Because once my code is compiled into machine language, it has no memory that this was called left, and this was data, and this was called right. It just knows, hey, the first thing I find is a pointer, the next thing is an integer, the next thing is a pointer. And if I actually have my structure set up somewhere else like this, it's going to think, okay, this should be a left pointer, this must be the integer data, this is the right pointer, and weird things will happen. So you want to be consistent with this, and if you put this declaration into like an include file, you don't have to worry about this. You just include that file every time that you want to use a struct node, and it's always going to be the same definition. So that's just a gotcha to watch out for. All right, so let's make a root node. So there's a struct node star root. Now, I know I want to call malloc. I want to set the size of malloc to the size of a struct node. And like that. And let's build a tree. So let's build a tree with a 40 at the root. So I want to say root arrow data equals 40. Alright, it's not drawn in the picture, but the fact that there's no children means the left and right children should be null. And it's really important, if you want something to be null, set it equal to null. And if you don't and you run valgrind, you'll get messages from valgrind about uninitialized values. And that's warning you that you're using something that you didn't give a value to. So I'm going to want to definitely say root arrow left equals null and root arrow right equals null. So there's no children on this node. Alright, so there's our first test program. We're just going to create a root node.
I have a question.
Yeah.
When we're creating these root nodes, I see that you're giving them a data, but what if that data needs to be used in part of the structure, that specific number, I guess? Do you just use a different kind of data that just won't be within the list?
Can you say that again?
Your roots data is equal to 40.
Okay.
What if 40 is something that needs to be, well, I guess...
Like a variable?
Included, wouldn't it?
It could be like a variable or something.
Okay.
If we don't want to just give it a value of 40. In fact, we're going to do that in a minute.
Sorry, I was thinking about it as like the 1, 2, 3, 4, 5, 6, 7, where it's not going to show up. I guess it would end up showing up, so it would be part of the tree list.
Yeah, it should.
Okay, cool, never mind.
Okay, no problem, it's good. Alright, so let's go ahead and compile this. Let's run it in GDB. Let's start it. We'll do the malloc, we'll set the root data, we'll set the left and the right to null. And so now if I print out root, it's got an address, right? This looks like a valid memory address from the heap. And I can see what this looks like because I'm in GDB and I compiled with -G. I can say, show me the thing that root is pointing to. So dereference root. And it gives me this nice presentation. Left is equal to 0x0. That's null. Data equals 40. Right equals 0x0. That's also null. So we've successfully created a root node. And if we wanted to just examine this memory location, we could say examine that location. And there's a 0 stored there, and it's followed by a 0, and it's followed by a hex 28, and a 0, and a 0, and a 0, and that's not terribly interesting. But we'll come back and look at this same view of memory in a few minutes and see some more interesting stuff. But this 28 hex, 2 times 16 is 32, plus 8 is 40, that's the data field. So this is, presumably the left child pointer, this is the data field, and some part of this is the right child pointer. Alright, so let's make this a little more usable, because what I want to do is I want to create an artificial tree that looks like this. I want to put a 40, a 20, and a 60 in there. Alright, so I don't want to keep typing this code in over and over and over again. I'm going to do this a lot though, so I'm going to make a function. And I'm going to make a struct node star new node. And I'm going to pass a piece of data to it. And in here, I'm going to make a struct node that's equal to the return from malloc, and I'll set the root data value equal to data. I'll set the left and right children to null, and I'll return that value. And this is initially going to be the root of our tree, but it's not magic, so let me change the name of this to, something like Fred. Right? It's just a local variable. And I'm going to declare a root up here in main, but it has nothing to do with whatever I call this. So how do I make a root node? Struct node star root, and I'm going to set this equal to new node 40. I'll be consistent. Space doesn't matter. So this will call the new node function, which allocates a chunk of memory, sets the data field equal to whatever I passed to new node, 40 in this case, sets the children to be null, and returns that node that was malloc. And so this will set root equal to a new node with a value of 40. So I could run this in the debugger and it would do exactly the same thing as before. So let's go ahead and tack on this other node 20 to be a left child of 40. So I'm going to call new node 20. That's going to give me a new node with its own data field of 20, left and right children of null. How can I make this be the left child of root? Any suggestions?
Wouldn't you need some kind of like add node function that takes in a root and then it makes it its left or right node?
I actually
What
don't.
nodes it has?
I can actually do this in one statement in C. And if you think about root, it's a node, it has a field called left, it has a field called right. I want that field...
dereference the left and then set that to the new node, right?
Yes. Dereference the left and set that equal to the new node. In other words, I can say root arrow left equals new node. So root is this block of data that contains, the 40 and the left and right pointers. The arrow says go to that block and find the field called left. Well, that field called left is a pointer to a struct node. Where is it pointing? Right now it's pointing to null. This will change that to point to whatever this is. What is this? This is the address of another node in memory that contains a 20. So this one statement says, basically take the root node's left field and have that point to this new node containing a 20.
Wouldn't you want some function to do that for you, though, in order to keep a balance?
Eventually we're going to make a function to do this, but right now we're just cobbling together a tree by hand.
Okay.
Just because that's easier to do. And similarly, I can say root arrow right equals new node 60. And those three statements should build this little tree. But I gotta prototype my new node function. Alright, so new node will create a node for me. And by the way, really common mistake, putting all your prototypes in the beginning of your program. Oh, that actually worked. My compiler, it doesn't work because it doesn't know what a node is yet. Alright, never mind. That's okay. But I'm going to put it down here anyway, after I've declared what a struct node is. Alright, so let's run this in GDB. And we'll make a new node, we'll make a new node, we'll make a new node. So now we can print out what root is pointing to. And it's a node with a data value of 40, but it has a left and right child that are not null anymore. So if I look at what the left field is, right, it's this address that left is pointing to. That should be the address of a node containing a 20. So if I print star root arrow left, there's the left node. It's got a data field of 20, it's got left and right children that are null. And if I print star root arrow right, that's a node containing a 60 and left and right children that are null. So we've made this little 3-node tree in memory now, and we built it by hand. And now if we examine this memory location in memory, it looks a little more interesting. It's got a 55, 75, 62, 80, followed by 55, 55, 28, 0, 55, 75, 62, A, 0, and 55, 55. So this is the 64-bit address corresponding to the left child of root. Right, it's 6 fives followed by 75, 62, 80. So these two words, these 8 bytes, correspond to the left field. And then this 4-byte number, this word 28 hex, that's the data field 40. And this 0, this is just padding. This is this alignment that it does where it wants addresses to start on at locations that are divisible by 8. So 6C is not divisible by 8, 70 is. So this is padding. And then this is another 64-bit, 8-byte address, 55, 55, 55, 75, 62A0. That's the right child's address. All right, well, let's finish up our tree. Let's put a 10 and a 30 and a 50 and a 70. And so we can just piece this together by hand. So root left left equals new node 10. Root left right is going to be new node 30.
Is that supposed to be root or reet?
Should be root. Thank you. And then root right left and root right right will be my 70 and my 50. Now this is not the way to build a big tree, right? But this is saying I want a tree in memory so I can play around with it. And particularly we're going to play around with printing it next. And so I want to do some print code. And so I'm just cobbling a tree together by hand, right? So if I start at the root and I go to the right and I go to the right of that, that's this spot right here, and I want to set that equal to a new node containing a data value of 70. Root right left says start of the root, go to the right. The thing on the left should be a new node containing a 50. So that's a painful way to build a tree, but it works for this. So there's what root looks like. Here's what root right looks like. It's a 60. Here's root right. Right. Thank you. Awesome. And here's root right left, and so on and so forth. Oh, thanks. So let's write a left node right traversal algorithm. So this is not going to return anything. It's just going to take a struct node pointer, which will be the root, and it will print out the data in order. First the left subtrees, then the root node, and then the right subtrees. And we're going to code this pretty faithfully from this 4-line algorithm that we came up with. If the root's null, just return. Otherwise, traverse the left subtree, print the root, traverse the right subtree. And if we do this correctly, it should print the data in order. That's why it's called in order. All right, so let's code this. So here's our in order traversal. So we'll take a root, we'll print it out. So we need our base case. So if the root is null, there's nothing to print. We're just gonna return right away. That's a root, not an rrot. Okay, otherwise, let's print the left subtree. And then let's print out the root node's data. And then let's print out the right subtree. And we'll be done. All right, let's see if this works. So I'm going to call LNR, and I'm just going to pass it the root. And I don't have any new lines in my traversal code. I'm just going to print things out on the same line. So I'm going to print out a new line at the end of calling my traversal. But this will basically print my tree for me. So you ready for this? Here we go. There's your tree data. And what's happening when we print this tree is pretty complex, right? We're calling print on this tree, which is causing a call to print on this tree, which is calling a call to print on this tree, which is calling a call to print on a null tree, and then printing the 10, and then printing this null tree, and then printing the 20 and calling print on this 30, which calls a print on the null tree to the left, prints the 30, prints the null tree on the right, and then it prints the 40, and then it does all of that again on this tree on the right. So there's a lot of calls being made here. But in the end, when we run this, there's our tree data in order.
Pure magic.
It is. Best kind of magic. Let's just print a star every time that we call the LNR function and see what that does. Right? So this is how many times this function is being called. And you can see it calls itself 4 times before we print out the 10. And then another call prints the 20, and then 2 calls to print the 30. Another call for the 40, and then 3 calls for the 50, and so on. This is the version of trying to understand recursion that will probably be pretty maddening, right? Trying to understand, well, why does it make 4 calls here, and 2 calls here, and 3 calls there, right? But we don't need to understand the exact order in which these calls are made and so on. What we need to understand is if this function really does print a tree, then these 3 lines of code will print a tree. This will print the left subtree, this will print the root, this will print the right subtree.
Kind of makes sense when you look at it for long enough.
Yeah, yeah. but then it might stop making sense for a while too. Now if I do pre-order, if I put my print statement first, my data comes out in a totally bizarre order. 40, 20, 10, 30, 60, 50, 70. And if I do post order, where I print my root data at the end, it comes out in a different order. But if I print my root data in the middle, that's called in-order traversal. That's what LNR refers to. And if I do that, my data should come out increasing from smallest to largest.
It seems like it would be really useful to draw more of like, I guess, the scope of the recursion. So like when you hit the bottom of the tree, when you hit 10 there, you're gonna do a return and then go back to a previous call of the function. And then when you hit return again, you're going to go back to an even further previous call of the function.
So
I think it makes more sense to think of it that way, right?
Yeah. So this is why octopuses would be good at doing this. Because, you know, you start off, you put a finger here and say, okay, I'm going to come back here. But first I'm going to, you know, traverse this tree. And you say, okay, I'll come back here. But first I'm going to traverse this tree. And you actually do another level here where you say, okay, I'll come back to this. First I'm going to traverse this null tree. All right, I come back here. Now I traverse this tree. Now I come back here. I'm done with that. Go back to the last place I remembered. That was right here. And now, you know, print the root and then do the whole thing on the right tree. And when you're done with that, come back up and say, okay, I'm done with the root, and go on. So the order of the traversal is actually something like, you know, visit this node, and then this, and then come up to the root, and then come down here, and then do that root, and then come down here. And so it's kind of a, and this is called depth first, because we go down, and the first node we're going to print is the leftmost node at the deepest level. We're going to come all the way down here, and then we'll hop up just a little bit, and we'll start going deeper again. And if there was other stuff here, we would print all of these and this before we came back up another higher level. And so that's left node right, which is in order. If we do printing the root node first, that's called pre-order. And if we print the root node last, that's called post-order. And this is the one we're most interested in now because it gives our stuff the order that we expect, in this case from smallest to largest. Now, what do you think would happen if I swapped the order of the left and right subtree traversals? In other words, traverse the right subtree. Good notion, but not exactly. So I'm going to traverse the right subtree first, then print the root.
Oh, we would get the exact inverse of what we've got so far.
Yeah.
From biggest to smallest.
Yep, because the right subtree contains all the stuff that's bigger. And so this will give us our list in decreasing order.
Magic.
Yeah. And so this would be called, that would be right node left. Do the right tree and then the root node and then the left. We don't usually do this. Usually it's one of these three, and most often it's left node right. But we'll talk about some applications for these other orders another day. So let me put this back to where it was. All right. So let's so that's some business with traversal. And we talked about how to search this thing recursively. And we talked about how to insert by moving down the tree and getting to a point where there's a null, and then putting our data there. But just like printing, traversing, just like searching, there's a way to think of inserting recursively. Insert, not instir. There we go. So we know we can do this whole business of, move down, move to the left, move to the right, and so on. If we want to move to the left and there's nothing there, add our new data at that point. But there's a recursive way we can think of this. And so let's make an insert root comma number. And the basic approach here, let's say we've got our big long hairy tree, right, that we were inserting things into. And let's say I want to insert, I don't know, let's insert a 37. Well, we could write a while loop, and we could use some temporary pointers. Start here, go left, go right, nothing to do, add it right there. But there's a simpler way to think of adding something to a tree, which is compare 37 to the root. 37 is smaller, so we know that we want to add this 37 into this left subtree. And so let's just use our insert function to do that. And so my insert code is going to look something like this. If our number that we're inserting is less than the root's data, insert that number into the left subtree. Else, insert that data into the right subtree. Nice recursive feel to it. We're not worried about duplicates here. We're going to assume our number is not equal to the root data. So if our number is smaller than the root, let's just insert it into the left subtree. Otherwise, we'll insert it into the right subtree. And this almost works. But there's one case where this will blow up. And that's the case where the root is null. Because if the root is null, this is going to throw a seg fault. And if the root is null, there is no left subtree to insert into. If we're trying to insert into a tree that does not exist, that has no nodes, we have to do something different. We have to actually create a node and make that the root of the tree. So we can do something like this. If root is null, do a malloc statement and set up the data field and all that kind of stuff. We've got a new node function for this. We can do that. But we want this to be the new root of the tree. And so here's the peculiar thing we do with this insert function, and this is fundamentally different from linked lists. We're going to have this function return a pointer to a struct node. And once we create a new root node here, we're going to say, let's return that. That's the base case. That's the thing that's going to save us from recursing indefinitely. So if we try to insert into an empty tree, make a new node, return that as the root. Otherwise, if our number is sitting to the left of our root, let's insert into the left subtree, and we'll just return our original root. Because if you think about how this insert works, once there's a root node, that never changes. Whatever we insert is going to be either something that changes over here or something that changes over there. The 40 is never going to change. So the only time we're taking advantage of returning the root is when we're moving from an empty tree to a tree containing one node. Alright, there's one other case we gotta take care of. Let's suppose our tree looks like this, and we're saying insert a 20. Okay, if the root is null, nope, that's not the case, it doesn't apply. If our number is less than the root data, well, our number is 20, the root is 40, yes. So we're going to insert 20 into root arrow left. Well, root arrow left is null, right? There's nothing to the left. So this call to insert is going to make a new node. It's going to put a 20 in that node, so we're going to have, you know, a 20 sitting here as a new node. And this call to insert is going to return the address of this node. But if we don't do something with that new node 20, it's not going to be part of our tree. And really what we want this to do is become, you know, the left child of the root. So insert, whatever it creates, has got to get linked up to our tree. So really what we need here is root arrow left equals insert. And down here we need root arrow right equals insert. And now we've got a good insert algorithm. So this is the most complex recursive thing we're going to do today. And it's an extra order of complexity because of this business right here. But the idea here is that when we're recursively trying to add, you know, a 37, we're going to come down here, we're going to come down here, we're going to try to insert 37 into this tree. We're going to make a call to insert on the right subtree, which is null. And the insert function will create a node containing a 37, and it'll return the address of that node. To hook this up to our tree, we need to not just call insert, but we need to say this node's right child should be 37. And that's what's happening right here.
Wouldn't we have another little if statement for a duplicate?
No duplicates.
Well, I mean, to avoid putting one in.
I don't want to go down that path, but yeah, we would need to do something.
Okay. If I follow this correctly, this would return the root, like the very root of the whole tree, once it's done, right?
It does, yes.
Okay.
And once there's a root, this will never change the root. But if the root's null, it will create a node and then return that root.
Neat.
Yeah. And yeah, you could put something in here. You could say if it's less than the data, if it's bigger than the data, if it's equal to the data, and do something there. But I just don't want to put it on here because it'll complicate it.
Gotcha.
All right. So this should work. And we've got 17 minutes. Let's code this up and see if it works. And I'll post this code in the shared code area on the server after lecture. But let's piece this together here. So I'll prototype the function. And my comment here is that, you know, this function will add a node to the tree, and it will return the root of that tree, which could possibly be a new root of the tree. In particular, if the tree was empty to begin with, if root was null, this will return something different from null. It'll return the root of the tree that we get after doing this insert operation. But we're going to fix in our minds the idea that insert always returns the root of the tree after we've added something to it. And if we believe that, then this is absolutely the right thing to do. Insert this number into the left subtree of root and have the left child of root be that new tree. And, you know, most of the time, this does not change root arrow left. But once in a while it does. And it's those few times when it does that makes the whole thing work. That's another way to sort of get lost in the rabbit hole thinking about recursion. But we'll just take this as, you know, this is the goal. Insert this a new node containing this data into the tree with this root and return the root of the resulting tree. And so this is a new function. I'm going to take out all of these calls that we had up here. And we'll just go ahead and print the tree contents there. All right, so let's go ahead and let's write this function. All right, so first thing we need to check for is a null root. If the root's null, we've got to make a root node. Right, so that's a pretty simple case. If the root is null, let's just make a new node containing data. I'm going to switch this to num because I called it num in the pseudocode. So let's be consistent. So if the root's null, we'll make a new node. We'll return that. All right, so that's this piece of the algorithm. And we've already got a new node function, so I don't have to call malloc here. Okay. Next possibility: number is less than the root node's data. So we want to insert to the left. So root arrow left equals insert root arrow left, comma num. And then I'm going to return root. All right, if our root was null, we returned right here. If our number was smaller than the root, we returned right here. If we get here, and we're assuming no duplicates, the only possible situation is our number is bigger than the root. So I'm not going to bother writing an if statement here, but I could say if number is bigger than root data. But we know that if we're here, number must be bigger than the root data. And so we're in this last case, we should insert to the right of the root and return the root. So I'm just going to say root arrow right equals insert root arrow right, comma num, and then return the root. And that's a pretty short function. And if you take out the spaces and the comments and the stray curly brackets, it's kind of like 3 lines of code. Right? Because I can do this in a single line, I can do this in a single line, and that's a single line. It's a pretty short function to write. But unless we did something silly, this should work. So let's see if it compiles. Alright, so it compiles, except I forgot about root in my main program. So let's look at our main, right? So I got rid of those things where we manually piece together a tree. So let's build a tree by using insert. And so I'm going to make a struct node pointer called root, and I'm going to initialize it to null. So we've got an empty tree to start with. So we're going to add some nodes. And when I call my insert, I'm going to have to say root equals insert root, comma, and, you know, put in a root node value. Well, if I do this, I should get a tree with 1 node in it. And it printed out 100. Well, that's not terribly impressive, but it didn't blow up, so I'm impressed with that. All right, so so we got 10 people in the room, so start shouting out your favorite numbers, and let's build a tree.
72.
36.
1.
3.
Cool.
Can we do negative numbers?
Sure.
Negative 80.
Nice.
486.
46. Maybe that was 486.
486.
All right.
$51.
Anyone else?
82.
82. I'm really getting lottery numbers from you, you know. All right, I'll make.
I've never won, so I wouldn't take that.
Yeah, but do you know what they say? You got to play to win.
Yeah, that's true.
All right. So here's some numbers. All right. So let's add these to our tree. And then let's go ahead and print the tree with our LNR function. And these should come out in increasing order. So let's try it. There we go. Not bad for like a 3-line insert function. So this is the power of recursion, right? To rethink of this problem of inserting instead of moving down the route and going left and right and all that kind of stuff. Think of it in terms of subproblems. If the route's empty, it's a simple problem. I'm just going to make a node, that's my tree. Otherwise, you know, I'm just going to insert into this smaller tree on the left. If my number should be on the left, if my number should be on the right, I'll just insert into this smaller tree on the right. And that magically works.
And so in the main program, you could have just implemented a while loop with fgets and scanf and basically just had a user build a tree by just inputting numbers, right?
Yep, definitely. And that's maybe very similar to what you end up doing in PA4. I haven't thought about the details of that yet, but PA4 will involve binary search trees, and we'll be doing a number of things with them.
I kind of am too.
It really is possibly the most generally useful data structure that we'll encounter. It's a superset of lists, right? But there's so many different versions of binary trees and so many ways we can organize them, and they generally lend themselves well to these kind of recursive algorithms, and that just makes them joyful to work with, but also very efficient. So think about the question of searching. And you know, I don't know how many nodes I have here, 15 or 20 nodes, right? But because it's a binary search tree, each time that I compare the number I'm searching to the root, I cut my problem in half. And when I throw away 1/2 of a tree, right, the tree that I end up with has a smaller height than the original tree, right? It's at least one level smaller because I don't have the root anymore. And so if my original tree has a height of 10, I know that after 10 comparisons, I'll be down to a tree with a height of 0. Which means I have a single node, and I just check that node to see if it's what I'm looking for or not. So this is this logarithmic hacking away of the problem space. And so, as I said, 1 trillion nodes, you can search with 40 comparisons.
Some time ago, I tried to implement some sort of very simple AI in a video game. And if I was to make like the decision tree we were talking about earlier, I never understood that structure at first, or why it would be very quick. But I think I could do it now with what I've learned today.
Awesome.
Which is super, super cool.
That's very cool. Yeah, so this would be a hard thing to start the course with, definitely. Um, Partially because there's all of these mechanics of, you know, mallex and arrows and asterisks and things like that. And refreshing or learning those with linked lists is a little more user friendly. But then once we start doing, you know, full on recursion like this, that's just a whole separate level of understanding. Um,
Well, you know, it's funny you said most of the stuff that we do in this class is going to get easier once we get the concept of pointers, and it's funny because that's dead on.
cool. Okay, that's good to know. Yeah, and really, once you're comfortable with pointers, a lot of computer science gets easier. And even when we move to languages like Java, where we don't have explicit pointers, being able to sort of think about pointers in the background actually helps with dealing with things like, you know, cloning an object and stuff like that. Um, so yeah, it's a good foundation to build on, I think.
Well, with Java, you're kind of pointing more to like classes and methods, right?
Mm-hmm.
Using the dot notation and things like that.
Yeah, exactly.
Okay.
And all of this stuff like malloc and such is done under the hood for us when we call a constructor. That's doing the malloc and initialization and so on and so forth.
We're kind of already doing that with init list and
Yeah, exactly.
list free.
Yeah, you're creating your own constructors.
Huh, I never thought about it like that, but I guess that's true.
Yeah, that's a cool way to think about it.
I've thought
So
of
this is very much like what you were talking about in calculus 1, where you're doing everything plus h and whatnot, and you find out at the end that you could easily do it in like 2 seconds.
Mm-hmm.
You know, with derivatives and whatnot. It's
Right.
very much true with this, and you know, doing Java at the same time. Is we're learning a lot of the same stuff that we're doing in the Java class, but we're learning the more technical way of doing it in this class. Then Java is just like, you don't even know what's going on.
Yeah, exactly.
Yeah.
Yeah, and that's an interesting experience that you're taking them at the same time because you get to see these things in parallel.
Yeah. Like I said before, it really helps with the recursion aspect because I didn't know what that was, and then we talked about it. And now we're actually like going a little deeper into it in this class, so it helps in both classes. You know?
That's awesome. All right, so that's some stuff to think about. And like I say, don't feel like you need to force yourself to understand it perfectly. It's a process, and it takes time, and it takes you know, going back and looking at it again and again. But we're going to work next week with other applications of recursion to trees. For example, determining the height of a tree, which is, you know, based on the depth of the deepest node. We'll see a real straightforward recursive way to do that. And then we're going to talk about the balance of a tree, how to tell if a tree is nice and full and fluffy, like this, or if it's, you know, something really sort of lopsided. Sorry, you know, a balanced tree like this, or something really lopsided, like this. This is still a binary search tree. If I pick any node, everything to the right is bigger, everything to the left is smaller. But this is clearly a different looking tree from this, right? This is what we call balanced. This is what we call not balanced or lopsided. And we'll see a formal definition for whether or not a tree is balanced, and we'll see how to make that a recursive definition. And then writing a function to test the balance of a tree will be trivial. It'll just be taking that definition and putting it into code. So we're going to play around with that stuff. We'll look at height, we'll look at balance, and then we're going to talk about deleting from a tree. And deleting from a tree is a lot different from deleting from a list because, for example, if I want to delete this 60, I can't just remove this node and free it, because what about its children, right? Where are those going to end up? And, you know, the 40 has a free right child, so it could adopt one of these, but it can't adopt both of them. And if it adopts the 50, where do we put the 70, and so on and so forth. So deleting from a tree is going to be a whole separate algorithm. That's probably the most complex algorithm for basic tree manipulations. But we'll go through that next week, and that'll end up being highly recursive also. So we'll get a lot more practice with recursion. We'll get deeper into some of these algorithms, and then we'll be ready for talking about balancing trees, which is sort of the really, really sophisticated tree manipulation algorithm that I don't think we'll code it, but we'll go through it in a lot of detail, and we'll look at pseudocode for it. So that's where we're heading next week or the week after. All right, have a great afternoon. Good luck finishing up PA3. See you in office hours tomorrow if you like. If not, have a great weekend, and I will see you next week.
Thank you. Thanks a lot.
Thank you.
You have a good day.
Have a
Thanks,
great
you too.
weekend.
Actually, Nick, do you have time to answer one question real quick?
Sure.